Good day, my name is Chin Wei Chong. This project is about designing a single-phase transformerless photovoltaic inverter with silicon carbide MOSFET. Recently, renewable energy, especially solar energy, has experienced rapid growth due to incentives from government and various advantages of solar energy, such as environmental friendly. In order to utilize the DC voltage generated from the solar panel, inverters are required. Conventional inverter is connected with a transformer for isolation and voltage step-up. However, it has high losses due to the iron loss and core loss in transformer, and the size of the transformer is big. So, researcher has proposed transformerless inverter such that the inverter has high efficiency and smaller in size. Diagram on the right is the transformer-based inverter, and the diagram on the left is an example of transformerless inverter. You can see that the transformer-based inverter is much more bigger. In transformerless inverter, without isolation of transformer, a parasitic capacitance will form between solar panel and ground, which lead to leakage current. Leakage current can cause electric shock and electromagnetic interference (EMI). Also, without transformer, the inverter requires high input voltage. To resolve these challenges of transformerless inverter, zero-state decoupling topology was proposed, such as H8, H5, and H6 to reduce the leakage current. Then, midpoint clamp topology was also proposed, such as ANPC, OH5, HVZVRD to eliminate the leakage current, but it requires many components. Also, to eliminate the leakage current with less component has led to the third topology, which is common ground topology, such as flying capacitor, charge pump. However, even though the leakage current was eliminated, but the transformerless inverter still requires high input DC voltage due to the absence of transformer. With the problem statement stated in previous slide, the aim of this project is to design a high-performance, single-phase transformerless photovoltaic inverter with silicon carbide MOSFET. There are three objectives in this project, which are to design a silicon carbide-based transformerless inverter, to simulate the inverter using Plex simulation software, to evaluate the switching loss, conduction loss, and efficiency of the inverter. This slide shows the circuit diagram of proposed transformerless inverter, which is constructed with 5 switches, 1 diode, 1 capacitor, and 1 inductor, excluding filter. The proposed circuit features no leakage current due to common ground structure, where the negative terminal of input and output are directly connected. Also, proposed inverter provide voltage boosting, which can resolve the needs of high input voltage of transformerless inverter. The diagram shown in this slide is the input-output voltage of proposed transformerless inverter, where the blue line is input DC voltage 50 volt, and the red line is output AC voltage 240 volt RMS. From this simulated graph, shows that the proposed inverter is capable of boosting 50 volt input DC to 240 volt RMS AC output, which validated the voltage boosting capability of the proposed transformerless inverter. The table in this slide shows the losses and efficiency of proposed transformerless inverter at different percentage of load at switching frequency of 50 kHz. Since the inverter is not always working at nominal power, therefore, it is more meaningful to evaluate the weighted efficiency of the inverter. California Energy Commission, or CEC efficiency, is one of the commonly used weighted efficiency standard for transformerless inverter. From the data in the table, the CEC efficiency of proposed inverter is 97.49%. As stated in problem statement, the leakage current in transformerless inverter can cause electric shock and electromagnetic interference. Based on the standard VDE 0126-1-1, stated that the leakage current must keep below 300 mA. In this slide, shows the simulated leakage current of conventional full-bridge transformerless inverter, which has a peak current of 340 mA. While H8 inverter, which is based on zero-state decoupling topology, has a 50 mA peak current, while the leakage current for proposed transformerless inverter, which is based on common ground topology, has a constant zero leakage current. This shows that the proposed inverter is capable to eliminate the leakage current. In terms of sustainability, solar energy is environmental friendly as it does not produce greenhouse gases such as carbon dioxide when generating electricity. Also, comparing to other renewable energy, such as wind and hydro, solar panel has no moving part, so it requires less maintenance and have longer lifespan as there is no wear and tear due to moving part. Next, the proposed PV inverter is constructed with 5 MOSFET, 1 diode, 2 capacitors, and 2 inductors, which lower the cost and reduce the size of inverter. Combining the advantages of solar renewable energy and the advantages of proposed inverter discussed in previous slide, this project helps to promote the use of solar energy and replacing conventional way of generate electricity to reduce the use of fossil fuel that release pollutant. In PV system, the solar panel can be connected in different configurations, namely string inverter and micro inverter. In string inverter, multiple strings of solar panel are sharing and common inverter. This type of inverter configuration has low efficiency and low reliability. This is because when one of the solar panel is affected due to shadow, the efficiency of whole PV system will be affected. Also, if the inverter is not working in the PV system, the whole PV system will be shut down. However, in microinverter, each solar panel has its own inverter, so when the solar panel is affected, the other solar panel will not be affected. Similarly, if the inverter is not working, it will not affect the other solar panel in the PV system. This makes microinverter has high efficiency and high reliability. The reason that's stopping the implementation of microinverter are cost, size, and voltage, as each solar panel requires one inverter and conventional inverter has many components and bulky in size. Therefore, it is expensive and requires large space to implement microinverter using conventional inverter. Also, voltage from single solar panel is unable to provide enough input voltage for the inverter to produce desired output voltage. However, the proposed inverter that uses less switch and featuring voltage boosting capability can greatly resolve these challenges of implementing microinverter. In PV system, transformerless inverters are preferable due to smaller size and greater efficiency. However, transformerless inverter systems are suffer from leakage current issue and require high input voltage. The proposed transformerless inverter featuring zero leakage current and voltage boosting capability with only 5 active switches has resolved this issue. As a conclusion, this project has successfully achieved the aim and objective of this project, and the problem statement made were properly addressed. Thank you.